Welcome everyone for joining us today for the seminar by Professor Emanuele and Professor Yi. And it's always an honor to have everyone here. And especially at this time, we have realized there are some new waveforms come around, and based on the delay-Doppler and the OTFS paradigm. So we think it's a good opportunity to have all the experts in the field to discuss the potentials and evaluating everything, and we can have a long discussion without time limitation. So this is the online seminar hosted by me and Weijie and Zhiqiang, and also by this OTFS-SIG. And I'm sure that most of you guys are also from this special interest group. And this interest group is aiming for discussing the major technical challenges and breakthroughs and applications related to OTFS and delay-Doppler technologies. And it's also based on the signal processing and computing for communication technology community, and also the satellite and space communication technology community. Okay, so if you are interested in joining our SIG, here are some details you can follow, and you can check out our SIG website. Okay, so without further introduction, today's seminar is about reflections on OTFS and the delay-Doppler communications, and will be given by Professor Emanuele and Professor Hong from Monash University. Let me give a brief introduction of the two speakers today. Professor Emanuele Viterbo has received a PhD degree in electronic engineering from Politecnico di Torino. I'm sorry for my Italian pronunciation. In 1995, and from 1990 to 1992, he was with the European Patent Office as a patent examiner in the field of dynamic recording and error control coding. From 1995 to 1997, he held a postdoc position with Politecnico di Elettronica, Politecnico di Torino. From 1997 to 1998, he was a postdoc with the Information Sciences Research Center at USA. From 1998 to 2005, he was an associate professor and then an assistant professor and then an associate professor with Politecnico di Torino. And from 1996 to 2006 to 2009, he was a full professor with University of Calabria, Italy. He's currently a professor with the ECSE department and the associate dean of the graduate research with Monash University. And his main research interests include lattice codes for Gaussian and fading channels, algebraic coding theory, algebraic space-time coding, digital terrestrial television broadcasting, digital magnetics, recording, and irregular sampling. He received a NATO Advanced Fellowship from the Italian National Research Council in 1997. He is an associate editor of the IEEE Transactions on Information Theory, European Transactions on Telecommunications, and the Journal of Communications and Networks, and also a guest editor of IEEE Journals of Selected Topics in Signal Processing on the special issue of managing complexity in multi-user MIMO systems. He has been an ISI highly cited researcher since 2009. Very impressive. The second speaker is Professor Hong from Monash University. She has received a PhD degree in electronic engineering and telecommunications from the University of New South Wales, Australia. She is currently an associate professor with the Department of Electronic and Computer Systems Engineering at Monash University. During 2018 to 2020, she was with the Australian Research Council College of Experts. Her research interests include communication theory, coding, and information theory with applications to telecommunication engineering. She was a recipient of Nectar Caron Earlier Career Researcher Award at Australian Communication Theory Workshop. Professor Hong is currently an associate editor for IEEE Transactions on Green Communications and Engineering, and was an associate editor for IEEE various communication letters and the transactions on emerging telecommunications technologies. She was the tutorial chair of IEEE SIT 2021 and the general co-chair for the OTFS workshops in the 2019 to 2022 at the IEEE Communications Conference, and also OTFS workshops in IEEE Vehicular Technology Conference, and also IEEE Information Theory Workshop at 2014. Okay, so today's seminar is going to present by both of the speakers, and during the presentation, we'll have several breaks because we'll cover a lot of different contexts. So if you audience, if you have any questions, you can approach me or type in the chat, and during the break time, we can go through the questions if we have time. Okay, so without further ado, please join me to welcome both of the speakers to give the speech. Okay, I'll stop sharing, and the stage is yours. Thank you very much.
Thank you, Shreya.
Thank you.
Thank you, Shreya.
Thanks.
Okay, so I think I will start, and I would like to thank the organizers of the SIG group, OTFS-SIG group, for organizing this seminar series. And this is the first one, so we are starting off, and we aim to give an overview of OTFS fundamentals, especially for beginners, so that then we will focus on the basics of the modulation waveform, the wireless channel, and the channel estimation. And then we'll give a sample of an application on satellite. But we'll try to keep it very simple, and I'm sure we will have more presentations in this seminar series where you will see more advanced topics in here. But we will be joining and having all the time discussions and over all these seminar series. Okay. So I called it Reflections on OTFS because I happened to be at the presentation in WCNC 2017 in San Francisco, where Coherent Technology disclosed their OTFS scheme. And it looked very interesting because it reminded me when I was working on OFDM, that's in 1992. And at that time, you would just read 5 papers, and that was all the literature available on OFDM. And so it was easy to start. Well, here it was 1 paper and to start off with OTFS. Now, more than 5 years have gone by, and we probably have a lot more papers on OTFS, and it's picked up pretty fast. Now, one thing I learned about OFDM as time went by is that more and different interpretations on understanding of OFDM can be. You can have different approaches to understand how an OFDM modulation works. You want to see, you will have, depending on your specific background, you will find your favorite way to understand it. So you can choose a more abstract way, a more mathematical way, a more signal processing way, a more implementation way, maybe looking at MATLAB code. Okay, so you will find a way in to start off, and then you will gradually be able to expand in other ways, because the more ways you understand OFDM or now OTFS, the better. Okay, there will be new ideas exactly from understanding the same object from different points of view. So we don't want to, we cannot say we have one way to explain OTFS. There will be many ways, and in that diversity there is a lot of richness. So encourage to keep your mind open. Don't stick on one interpretation. So this is why this seminar series is really important. It's valuable. So as I said, our approach for today is to go from, let's say, bottom up. We will look at the various items of the various blocks of an OFDM OTFS system, including channel estimation and detection. Next slide, please. Okay, so a little bit of advertising. So during lockdown, which was pretty long here in Melbourne, we had some time to meditate about writing this book on delay-Doppler communications, and where we explained our views, our way of understanding OTFS, and it's been already a year and a half or more, almost 2 years, I would say, that and it's been adopted for people starting studying OTFS, and I personally use it in this IEEE Communication Society online course, which is an online course organized by IEEE Society. And I've done this course a few times in the past few years. The next edition will be in July. So it's over 3 days, 3 sessions of about 2.5 hours each, where I actually go into the details following our book and even some derivations of that you can find in the book. So for now, this is going to be a higher level presentation. For if you want more details, you can look into the book or you can attend this online course. So that's all for advertising for today. Okay, so this is I'll keep this short because probably it's less interesting, but for this audience, I mean, the idea is that every generation of wireless networks has had their own waveform. And starting from analog in 1G to narrowband TDMA in GSM, and then spread spectrum CDMA in 3G, and then finally in 4G, and now also in 5G, OFDMA. So wideband OFDMA has been there. Now, why did we change waveform every time? Not because we just wanted to change, but because there was a demand, a use case that really needed an improvement in the waveform. So where are the kind of boundary limitations in the current waveform, the OFDM waveform, and what could be the next generation use case that requires to change this waveform? Well, we can see in the next slide. Sorry, next slide. This is the scenario we want to look at. We call this the high mobility communication scenario, where there are a lot of moving transmitters, receivers, scatterers in the scene. So your wireless channel is a rich multipath channel where not only where the paths are not only static, but they change with time. And due to that, you have 2 effects occurring, which are dominating the channel behavior, which are the delays of the path and the Doppler shift of each path because of these different scenarios. Now, obviously, if when the Doppler shift occurs is due to mobility, and the speed matters. The larger the speed of any item in the scene, the larger will be this Doppler shift. And the fact that there are multiple paths, each with different Doppler shift, makes this OFDM struggle to work in such scenarios. So I think we can move to the next slide. And I just want to recall the two parameters which characterize a multipath channel. First one is the delay spread, and the reason we are interested in the delay spread is that the received signal is always a linear combination weighted by different path gains H1 and H2. It's a linear combination of two of the transmitted signal shifted delayed by a certain tau1 delay for the line of sight path, and the tau2, which is the other reflected path, which is longer. And when you see this, you write the received signal in this form. Actually, if you think of it as a linear channel, you can say that it's the received signal is the convolution of the transmitted signal and a tap delay line where the taps occur at the different delays and the coefficients are constant. Okay, so this is a tap delay line which is describing the power delay profile of the channel. So there is one tap for each path. Next slide is the other term, the other important effect occurring in this channel is when there is mobility. So if you have these cars with this, at velocity v moving directly along the line of path towards the base station, the receiver here, or the transmitter, the transmitter is here. The car will perceive a carrier frequency slightly shifted, and that's because the car goes towards the transmitter. And in particular, the frequency shift of the carrier frequency, which is called the Doppler frequency, is given by the carrier frequency times the speed of the car, v, divided by the speed of light. Now, speed of light is very large compared to the actual speed of the car, so this is a very small number. However, the carrier frequency is large, maybe gigahertz order, in the order of gigahertz, so you can see that the residual Doppler frequency can also be relatively large, even if the v is small. Now, there is one more effect you need to take into account, is that this Doppler shift is when the car is aligned with the path. But if we look at the reflected path, the actual speed that matters is the component of the velocity in the direction of the reflected path. So you have this v cosine theta, and then which tells you that the car is going to receive many paths, and because the paths have different angles of arrival, they will have all different Doppler shifts. Okay? So what does the received signal look like? So it's going to be a sum of obviously scaled gain by the gains h1 and h2, but and delay is the same tau1 and tau2, but then there is this term due to the Doppler. And what does this Doppler shift cause? It's like having a complex sine wave at the frequency of the Doppler shift, which is changing the taps of this tap delay line. Now, this is going to be a time varying tap delay line because of this term. You see the dependence on time. Okay, so next slide, we can see in general, this was just to show you the two ingredients, the delay spread and the Doppler spread. So the Doppler spread is the difference between the difference between the smallest Doppler and the largest Doppler, to make it simple. But in reality, the actual channel can be, if we look at it in continuous time, we can represent this multipath high mobility channel in this time delay and time. What does it mean? It means that the channel, if I freeze the channel, if I look at the channel, let's say today, I get an impulse response. Here is this one. If I look at it in 1 hour, it may be different. Okay, but this is now reduce the scale. These may be in milliseconds. This axis could be in the order of milliseconds, and then this could be maybe in the order of microseconds. This axis, and you can see that the channel is actually changing in time, so it's time varying. At every time you pick, you have a different impulse response of your channel. So this is how to interpret the delay time impulse response. Next slide. Okay, so what goes wrong in OFDM? Okay, essentially, just a quick recall of what is OFDM. You essentially divide your frequency band in a number of multiple parallel subchannels, which are preserve their orthogonality even going through a multipath channel. And the reason is that we add a cyclic prefix to the transmitted signal, and that allows for the subcarriers, subbands to remain orthogonal at the receiver, even if there is some delay spread in the channel. The trick is to make the delay spread, the cyclic prefix, just longer or equal to the delay spread, maximum delay spread in the channel. So next slide, I'll show you what happens if you have some Doppler effects. So because of the Doppler, the subcarriers and actually the subchannels lose their orthogonality. So you get some intercarrier interference, and you can kind of visualize it in this form. It's the sync pulses that don't align properly. So you get they cause, when you sample one, you get some interference from the adjacent all the adjacent subchannels. So that's the ICI, and that's the problem in OFDM when you have multipath Dopplers. Next slide. So this is, in summary, that's the problems of OFDM are, if you have these intercarrier interference, when it's severe, then it's very difficult to equalize the OFDM, because the single tap equalization will fail because there is a large intercarrier interference. The other known limitations of OFDM is that if you take uncoded OFDM, the performance is dominated by the worst subchannel. So and that's why in practice we use coded OFDM, or we do some kind of pre-coding to make our channels the OFDM more robust. But that requires additional complexity to the OFDM. So OTFS was proposed to solve these two problems of OFDM, and specifically it works in this new domain. So OFDM works in time frequency, right? You're putting your information symbols in a time frequency plane. In OTFS, the idea is to put the information symbols in the delay-Doppler domain rather than the time frequency. And this was first demonstrated in the presentation at WCNC that I happened to attend, and I thought it was very, very nice. It took me a while to understand why it was working, and I thought this, and probably many of you have gone through the same process. Understanding why it works takes some time, but there are some easier ways to understand. You will see, you'll pick your favorite way to understand how it works. I'll hand over, if now maybe any questions to this point, although it was just introduction. Otherwise, I can hand over to E to continue.
Hi, Professor. I think we have collected several questions. I'm going to read some of them. And there was one question regarding the advantages of OTFS application to high frequency, say 3 Hertz, in 3 Hertz to 3 megahertz to 30 megahertz, and it's more about mainly about the Doppler frequency resolution. That for example, if the Doppler effect, the Doppler frequency resolution that is relatively easy to achieve is 10 Hertz, and the normal Doppler spread is at 0.1 to 10 Hertz. The normal Doppler shift is up to 30 Hertz. So given the simple rate in this kind of frequency, is there any advantage of OTFS in combating Doppler effect?
I probably, I don't know, is this a written question? Is there a way you can share the chat?
Sorry. Yeah. I'm
Because
going
maybe
to. Yeah.
if you
So
paste it in the chat, it would be nice.
yeah, it's
But
already in the
anyway,
chat.
I think maybe it will, some answer to this will probably be a bit more clear in the next section where we'll talk about the resolution of delay-Doppler resolution that matters. And the one thing to say is, obviously, the higher the carrier frequency you're using, the larger will be the Doppler shift. Okay, so and what matters, that ICI that I showed you that disturbs OFDM, what matters is how big is the Doppler shift compared to the subcarrier spacing. So specifically, if you have a 1%, a Doppler shift which is less than 1% of subcarrier spacing, you probably can compensate that, and you can treat it as just little noise in OFDM. But if you have anything more than 1% of Doppler shift, your Doppler shift is more than 1% of subcarrier spacing, that equalizing that becomes very difficult in OFDM. So you're not able to equalize it as well. And that's where OTFS can do better, because it can resolve more paths, because a path can have multiple Dopplers. A path with the same delay, two paths with the same delay can have different Dopplers, and they could come from two scatterers which happen to be at the same distance, and but they have two different speeds, or even slightly different angle of arrival of the same from the same scatterer will generate two paths with the same delay but different Dopplers. So you can have situation where you have multiple Doppler. If your Doppler resolution, and you will see it later, is small enough that you can put one Doppler in one bin and the other Doppler in the other bin, it means you can resolve it, and that means you can effectively have the gain by combining coherently all the power coming from all the paths, even the delay-Doppler paths. But maybe I'll let this hand over to E, and she may give you a better understanding of this in the next slide.
Right.
Sorry, is there any other question?
There's another question, and it's asking by one of the students. I think her question is about the flexibility of OTFS in comparison to OFDM. So in industry applications, sometimes the OFDM symbol duration can be adjusted. However, in terms of OTFS, it always has a very long frame length in comparison to OTFS, in comparison to OFDM. Is there a possible solution for maybe the latency issue or the flexibility of the frame design for OTFS?
That is correct. The problem is that you can do, if your OFDM fails because there is too much ICI and you cannot correct it because there is a lot of multiple Doppler shifts, then it's not a fair comparison. So what you pay to fix that problem is the fact that you must process a frame which can be 10 milliseconds, can be even 1 millisecond. Okay, you can scale things to fit into 1 millisecond of a frame, but you don't have the granularity of time, of choosing shorter times, because OFDM is not going to work, because you don't have, and the Doppler will make it very hard to undo, to equalize that channel.
Thank you for the answer.
Again, I think these are maybe also questions that you will try. Keep that question. If you still have some doubt after E's part, we can resume it again.
Yeah, thank you for the answers. I also have a personal question regarding this question.
Please do.
Yeah, so I also got this question from from different people, and so it's mainly, as you mentioned, that in the higher frequency there will potentially be higher Doppler, which is correct. However, at the higher frequency bands, you're supposed to have a higher bandwidth. That means you will possibly have a higher subcarrier spacing. So the percentage of the Doppler compared to the subcarrier spacing may be smaller. So is there a general
But we are greedy, you know. Look what happened in optical fibers. In optical fiber, they always said, oh, there's so much bandwidth, we don't care. Now they care. So at some point, you will also care about saving bandwidth at 30 gigahertz, okay, at millimeter wave. You know,
that's right.
Because remember one other thing, that bandwidth cost processing. So to process a 20 megahertz bandwidth, now we do it, and we do it regularly on our phones. So it's doable. But processing a 1 gigahertz bandwidth will cost you a lot more of AD conversion, and basically all the baseband processing is 100 times more. So you can imagine that impacts on the battery life and everything. So saying that you have a lot of bandwidth, I would be cautious about that. So you still should care about that. Yeah.
Okay. Thank you for the answer. I think we have no questions so far. Please keep going, and
so
they will be...
go ahead.
Oh, okay.
Okay.
Please.
So I will talk about wireless channel representation. So let's first look at the different representations of linear time variant wireless channels as shown in this diagram. So we start with the traditional time variant channel impulse response, GT-TOR. So based on Fourier transform along delay axis, we can convert the channel response from time domain to time frequency domain to have the time frequency channel response, HTF. So this is associated with the OFDM technique. And we can also, based on Fourier transform along time axis, to convert the time variant channel response to get the delay-Doppler channel response, H-TOR-V, which is associated with OTFS. So next, we're gonna study the relation between time frequency and delay-Doppler channel responses. So the reason we want to study their relation is simply because we want to establish the connections between delay-Doppler and time frequency domains. So their relations are explained in these two equations. For instance, given a time frequency channel response, HTF, so you take two-dimensional Fourier-based transformations that involves both terms, Vt and F-TOR, and there's a minus sign in between, and that is called the 2D symplectic Fourier transform. And based on this transformation, we can convert time frequency channel response to the delay-Doppler one, and vice versa. So after introducing their relations, so now we narrow down to the delay-Doppler channel response of a specific channel. For instance, a multipath channel P-paths with parameter, the path gain Hi, delay tau I, and Doppler shift Vi. And then we can write down the delay-Doppler channel response as the summation over P path, and each path you have equivalent path gain Hi prime, delay tau I, and Doppler shift Vi. And next, what we're gonna do is to make a plot of the delay-Doppler channel response. And at the same time, for the same channel, we also make a plot of time frequency channel response so we can have a comparison. So in figure A, we observe that time frequency channel response get dense, and also it rapidly changes from time along time axis and frequency axis. So once we convert to delay-Doppler domain, and surprisingly, the delay-Doppler channel response becomes sparse and is time independent once you fix one delay, and basically you can get the corresponding Doppler shifts. So that motivates us to study and work in the delay-Doppler domain for the time varying channel with the severe Doppler shifts. So then up to now, what I'm talking about is the delay-Doppler, is the continuous time channel representation. So next, I'm going to introduce the discrete time channel representation. So after receiver sampling, so we basically can use either time frequency or delay-Doppler grades to represent the discrete time channel representation. So we start with the time frequency grade. So in this grade, basically we have n equally spaced time slots, each occupy t second. And along frequency axis, we have m equally spaced subbands, each occupy delta f hertz. So delta f is just 1 over t. So then after we performing the symplectic symplectic Fourier transform, we can convert time frequency grid to the delay-Doppler one. So in the delay-Doppler grid, there are n equally spaced delay-Doppler levels, each occupy 1 over nt hertz. This is called the Doppler resolution. So along delay axis, there are m equally spaced delay intervals, each occupy 1 over m delta f second. So this is called the delay interval. So then next, we're going to use this delay Doppler grid to represent the delay Doppler channel response given here, which is the summation over p path, and each path have equivalent path gain hi prime, delay tau I, and Doppler shift vi. So to represent it, we first assume this delay Doppler grid has sufficiently high delay and Doppler resolutions so that this p path can be equivalent represented by these p distinct grid points. So if we have an imagination on the third dimension, you're going to have p impulses represent corresponding path gains. So for instance, this point represents the ith path. Okay, so then you can identify the corresponding delay and Doppler indices and multiplying them with the corresponding delay and Doppler resolutions gives you the delays and Doppler shifts of that path. So in this way, we will be able to represent the delay Doppler channel response using the delay Doppler grid. So this is about wireless channel part. So I will go on, yeah?
Yeah.
Yeah, so next I will talk about OTFS modulation. So basically, I will start with the 2017 OTFS modulation demodulation structure proposed by Hadani et al. In WCNC. So later, when we were working on this topic, we also identified that this structure can be simplified to a simple version. So I will talk about that simple version in a couple of minutes. So as shown in this diagram, we first place the information symbols in the delay Doppler domain of size Mn. And then we apply inverse symplectic fast Fourier transform, which converts information symbols from delay Doppler to time frequency domain. And then we apply Heisenberg transform, which is equivalent to impulse shaping and OFDM modulator that converts time frequency samples to time domain signal. Then we can move on to the receiver side. After receiving time domain signals, we apply Wiener transform, which is the opposite function of the Heisenberg transform. So which is equivalent to impulse shaping and OFDM demodulator that converts time domain signal to time frequency domain samples. Then we apply symplectic fast Fourier transform to convert further to delay Doppler domain. So basically, in this red frame, it contains all the delay Doppler domain operations. And in the blue frame, it contains time frequency domain operations. And in the green frame, it contains time domain operations. So as Emanuele said, how do we understand OTFS? There are so many ways of understanding OTFS, depends on your background. So I assume you are all familiar with OFDM. So I list a simple understanding for you to start with. That is, the OFDM is OTFS is equivalent to an OFDM with 2D unitary precoding, ISFFT, in the time frequency domain, which spreads its information symbols equally in M subcarrier and N time slots. Okay, so based on this structure, we will be able to derive the input-output relation in delay-Doppler domain. So we first assume a noiseless case and also make assumptions of ideal pulses. And this assumption implies that transmitter and receiver use ideal pulses which satisfy perfectly the bi-orthogonal condition. And then the time-frequency input-output relation is simply the product of the time-frequency channel response samples and time-frequency data samples. So then we further convert this relation to the delay-Doppler domain. And this relation is it's simple, and it is nothing but the 2D circular convolution between the channel and information symbols. So how do we understand this 2D circular convolution? So I illustrate this by using the following examples. So in figure A, basically, we can place information symbols in the delay-Doppler domain with equal spacing. And then we transmit them over the delay-Doppler channel with channel response as shown in figure B. And then at the receiver, what we received is a collection of the spreaded information symbols. And by using the detection method, we'll be able to recover the information symbol. So of course, this is just a simple intuitive example that demonstrates the 2D circular convolution operation. So in reality, of course, you can place information symbols next to each other in the delay-Doppler domain. And then at the receiver, you will receive the overlapped spreaded information symbols. But by choosing the suitable detection methods, we can detect the information symbols. And this is a quick overview of the input-output relation and the ideal pulses. So now we replace ideal pulse by rectangular pulses, and then we continue our derivation. Basically, the time-frequency input-output relation, as shown here, it does has the both ICI and ISI. So it does have both ICI and ISI interference. Okay, so then we further convert the domain to the delay-Doppler domain. And surprisingly, the input-output relation is simple. It's a 2D twisted circular convolution. So compared to the previous input-output relation, simply what extra term here is this alpha term, and we call it the phase shifts. And these phase shifts, extra phase shifts, is incurred due to the ICI and ISI. And as shown here, these simple phase shifts in delay-Doppler domain are associated with the channel delay and the Doppler indices, Li and Ki, and also associated with the symbol location M and N in the delay-Doppler domain. Okay, so at the receiver, these phase shifts can be easily corrected. So then basically, this is a very high-level overview of the input-output relation in the delay-Doppler domain for OTFS. Yeah. Shall I continue this OTFS structure? I just finished this and we can have some questions. Yeah.
Thank you.
So as I mentioned before, that this OTFS structure can be simplified. Okay. So I will talk about this simplified version. So to talk about this simplified version, I first recall this 2017 OTFS structure in the left-hand side. And different from previous diagram, and in each block, I placed more detailed operations. So let's start with the information symbol in the delay-Doppler domain of size Mn. And then we process them by using the row-wise endpoint IFFTs and followed by the column-wise endpoint FFTs. So these two operations forms the ISFT operation that convert information symbols from delay-Doppler to the time frequency domain, and then followed by the column-wise, Heisenberg transform, which is column-wise endpoint IFFTs, then followed by parallel serial and adding CP for transmission. So here, if you look at these two operations that involves ISFFT followed by Heisenberg, so we also call this a two-step OTFS. And then in particular, if you look at the ISFFT second step is the endpoint FFT, followed by Heisenberg endpoint IFFT. So these both operations can be canceled out. So this structure is reduced to the right-hand side. So simply is the information symbols in delay-Doppler domain are processed by row-wise endpoint IFFT, followed by the column vectorization and adding CP for transmission. So that means you take each column vector and pack them to form a longer sequence and adding CP for transmission. So then for this simplified structure is nothing but the ZAG transform. So mathematically, we can represent as follows. So we have the information symbol matrix in delay-Doppler domain represented by X. And then we process them by using row-wise IFT represented by this FN dagger and followed by the column vectorization. So this is particularly called the inverse discrete ZAG transform. And if you look at this simple structure, okay, so we also call the one-step OTFS, and this step is using basically the inverse discrete ZAG transform. And this is a simplified OTFS modulator structure. And also, it is worth mentioning that this simplified structure is equivalent to the known vector OFDM, or so-called AOFDM, in these first two reference papers, which were proposed for static multipath channel only, but not studied for the time-varying channel with the severe Doppler shifts. So their relation with OTFS is studied in our formal work. So when you change the channel to a time-varying channel with a severe Doppler shift, so the system input-output relation would be different, and the channel estimation and detection would be significantly different. So that motivates us to study further this technique. So this is all about OTFS modulator part. And now we move on to talk about the demodulator. So similarly, this demodulator can be also simplified as shown here. Once we obtain this time domain signal by removing CP and serial to parallel, basically we can reform the delay time received signal matrix, and followed by the row-wise endpoint FFTs, we can convert it from delay time to delay Doppler domain. So mathematically, we can write down as R, which represent the time domain received the signal vector. And after devectorization, we forms the delay time domain received signal matrix, and then process it with the endpoint, the row-wise endpoint FFT represented by Fn. And this is called the discrete ZAG transform. So for ZAG transform, the properties were first discussed by Saif in this first reference paper. And later, we also summarized in our book. So this is about OTFS modulator and demodulator study, okay, in terms of ZAG transform. So basically, next, I will talk about the channel matrix representation. The reason I introduced this part is because it leads to an important conclusion, which is useful for the design of channel estimation and data detection. So let's first look at the received signal in the time domain in vector form. Assuming no noise basically is the product of the channel matrix G and the transmitted signal vector S. And the G is the channel matrix, which is a square matrix of size Mn. It can be represented by this expression, which is summation over p path. Each path have the path gain hi prime, followed by delay matrix pi Li and Doppler matrix delta Ki. So this pi is the permutation matrix given here, and Li is the delay type. So pi to the power of Li, that means they're gonna have Li times forward cyclic shift of the permutation matrix. And the delta Ki is the Doppler matrix, is diagonal. And basically each of the element is associated with the Doppler type Ki. So when we multiply G with the transmit signal vector S, what does that mean? It means that this transmit signal vector experiences Li times forward cyclic shift and then modulated with a carrier at frequency Ki, which is associated with the Doppler shift. So this is the time domain channel matrix representation. And next, we're gonna convert to the delay Doppler domain. And this delay Doppler domain channel estimation, channel matrix, I skip the derivation. I directly comments on the final expression. So the delay Doppler channel matrix is a summation over p path, and each path have a path gain hi prime and times the path matrix Ti. So in this paper, we have studied this Ti matrix. We find this matrix has only one non-zero element in each row, and position value of this non-zero element depends on the delay Doppler values. So we also identified this one non-zero element in each row. The location of this non-zero element in each row is unique. So this is good news, because after that, we make a summation over p different paths, and the overall resulted channel matrix will only have p non-zero entries in each row and column. So it implies this channel matrix H has a simple sparse structure. Okay, so thanks to this channel sparsity, we will be able to design properly the channel estimation and the detection methods. So you want me pause here or?
Thank you for the presentation. We have collected several questions. I guess maybe it's okay to ask if it's okay for both of you.
Mm-hmm.
Yeah, and so I noticed that Emanuele has already answered several questions. I'll just take some of the questions that has not been answered so far. Apparently, there was one question regarding the different domains of the channels. So we have introduced the channel in delay Doppler and time delay. People are wondering if the channel in frequency Doppler will also have some advantage for signal processing.
This we never explored. We never explored. I think most of the later we talk about channel estimation, and Emanuele will talk about detection.
Right.
So mainly we focused on delay time and delay Doppler, and sometimes even for specific channels, we even go back to time domain to do some estimation detection.
Yes.
So frequency and Doppler, maybe it's good for like underwater communication. You have extreme Doppler scenarios.
I agree.
But I really have no idea. I've never explored. Shuaiyang, have you tried?
No, I also thought about it. I think it's because it's the dual domain of high Doppler. I mean, given what OFDM behave well in time frequency, right? Like that's mainly for the delay only channel. So if there's a Doppler only channel, I guess frequency Doppler may have some advantage there, but it's not explored so far. I agree with you.
Yeah.
Yeah.
So maybe some smart guys in the audience may explore the remaining domain.
Yes, of course.
It's like people want to go from Earth, go to Mars for a nice escape. Yeah.
Yes, yes. We have also a question regarding these channels. Where people are asking, after post shaping, is it still valid to say that the people in the channel in different domains are equivalent? For example, I think what they want to say is like the effective channel after post shaping, is it still we can say is equivalent in time domain or delay-Doppler domain? I guess maybe because the post shaping is in the time domain. After converting to the delay-Doppler domain, it may not be exactly the same. That's the question they want to ask, I think.
Emanuele, you are muted. You're muted.
Yes.
Sorry, I'm here. I was talking to muted. So the answer probably to that is, if we look at, when we look at discrete time, we assume that the sampling frequency is Nyquist sampling frequency, limited, band limited, and then the real reconstruction pulse will have to be a sync pulse, right? Then that would be ideal reconstruction. So anything happening under that condition, that's ideal condition, will be reflected by the delay-Doppler in the delay-Doppler domain, exactly the same. Of course, if you don't use the sync reconstruction pulse, which gives you the band limited, first of all, you will have an out of band channel, and then also you will also have out of extension in time, because when you do a truncated filtering, you will have truncation in time. Yes. So given that, if you can still see what happens in delay-Doppler domain, but it will have some distortions. So
So I think they changed the input-output relation. We did this work. Yeah.
Yes. You do say you can see what happens with different pulse shapes and how you apply them. That's a lot. There is a lot of ways to apply the different pulse shaping in different domains. You can realize this filtering, but in the end, it's, if we reason as discrete time, and then we do, in theory, we have an ideal pulse to reconstruct, and that's where it is. Once you don't have that ideal reconstruction, then you have to deal with that. And the theory is there in the ZAC transform, but you have to go maybe to the continuous time ZAC transform, maybe, I don't know. That's harder to explain.
I agree.
You do lose some orthogonality. You do lose some orthogonality if you truncate, if you don't use this ideal. But I mean, it's also what is happening in OFDM. After all, just because it's OFDM, but even in OFDM, you have you have to go to the time domain. You need a reconstruction pulse. You will have some loss of, or minor loss of orthogonality, because your reconstruction pulse is not ideal. You will have some out of band because your pulse shaping is rectangular, or non sync, non-ideal truncated sync, or any Nyquist pulse. So that will always be a problem there, and it doesn't matter in OFDM. So because we are kind of used to the fact that in OFDM we put some guard bands. So we never use all the subcarriers in OFDM. We put some zeros. So in that way we have some guard bands, and that gets absorbed. And this will be probably the same thing would happen in OTFS. But in OTFS, we do have that CP, which kind of helps a bit, but then you may have to put an extra guard time between the frames to absorb any delay of the reconstruction filter, the real reconstruction filter.
Thank you for the answer. I personally agree with you. I think that's correct. Also, as you have mentioned that about the CP, there are questions about asking about what's the CP do in the OTFS modulation, especially because the time delay becomes a phase shift in delay-Doppler. So what's the CP? Do we still need CP?
You need the CP. Look, this is a multipath channel. Okay, any multipath channel, you want to wait until all the echoes have arrived, all the path delayed paths have come to the receiver before starting a new frame. So in OFDM we put a CP, and in that CP we kind of wait for all the paths to extinguish themselves at the receiver. In the good thing of OTFS is that we only need to put this CP at the end of the frame, and this is because then one OTFS frame will not interfere with the next one by having that CP. By the way, there are kind of 4 different variants of OTFS depending on where you put the CP. You can have a cyclic prefix, or you can do 0 padding instead, and then you can also put CP or ZP after each block, and that's one case that I will discuss in the detection later. Yeah.
Yeah, thank you.
Yeah, so it really depends on where you put it. You can put at the end,
But
protect
it's
the whole frame, but you still have ICI, ISI, and as I mentioned, the input-output relation, you can, at the receiver, you know all these delay-Doppler indexes and the MN of the OTFS, the information symbols location, you can compensate that. Or you can put each block the CP, so you can mitigate a bit ISIs between block to block, but eventually, basically, this I would go to save spectral efficiency. I would put CP or ZP at the end of the frame.
Yes, thank you. There are also questions regarding the channels, especially on the slide 14. People are asking if the delay and the Doppler are constant with respect to time.
Which channel? Which slide?
Slide 14.
You have to go back 14.
14. Sorry. You, hey? Oh, sorry, I went up.
The other way.
So, what is the question?
So are we assuming that each path has constant delay and Doppler coordinates in respect to time?
Within one frame. So yeah, I think the answer is one frame. In one frame, we assume the delay and the Doppler are fixed for the duration of one frame. And this means if my frame is a 10 millisecond frame, most high mobility Earth-like speeds will be constant within 10 milliseconds. In fact, we talk about the geometric stationarity, the stationarity of the geometric channel. So the path don't really change, and you can decide.
This is
you can assume this. This is the assumption of from one frame to the next, you can change delays and Doppler. So there may be a slight change of scene. The things have moved, but in the next frame, then you can estimate the new delays and Doppler and all the paths, and still run it. So every frame you can have a different value as long as they are constant within the frame. That's important.
Yes. I also have a follow-up question regarding this channel model. I personally agree with your explanations on this stationarity geometrically, and I want to mention there is also some certain type of channel may have several clusters. So there are sparse in terms of different clusters, but within each cluster there are many paths. Is there any advantages for OTFs to apply in such cases?
Well, it's the same thing happening if you look at the power delay profiles, and then there are clusters of delays, right? And then, but even if you're using OFDM, ultimately, or even OFDM has a limited time resolution of the multiple paths, and it's going to aggregate all the paths within the delay resolution, which is just 1 over the bandwidth. So the 1 over the bandwidth gives you the delay resolution of the different paths. If you have 2 paths which are within that resolution, you cannot distinguish them, so they overlap non-coherently, and you're going to get the resulting additional path. But that's again, it's something that's happening equivalently in OFDM, and people don't really care about it. So for the same reason, I don't think we should worry too much about it in OTFS. It depends, obviously, the resolution. The higher the resolution you have in delay and in Doppler, so if you can increase the resolution, you will resolve more paths. And when you resolve more paths, you collect all the energy from all the paths and recombine it coherently. So the nice feature of OTFS that all the paths that you receive, you can extract the information from all the paths coherently. So you don't get any cancellation across the path. But if whatever happens within one bin, there you get the result of the sum of all the paths in that bin, and you will represent it as a single path. That's always the case, because eventually the physical channel is continuous time, but the digital receiver can only see the samples. And once you get the samples, you have a limited information about the continuous time.
That's right. Yes. And there is a follow-up question on this cluster channel. Can we still assume that after non-coherent combining of all the paths in the same bin, can we still assume it's a constant over the frame?
Sorry, I didn't get the...
I mean, like after this non-coherent combining due to the clustering, so can we still assume this whole response of this effective path is constant in time?
Well, no, but because the gap between, let's say you have 2 Dopplers which are so close that you cannot distinguish them. If you add these two Dopplers, which are very close, it's like adding 2 sine waves with very close frequencies. They beat, okay, and then you will get the sum and the difference. Forget about the sum, but the difference is going to be a very slow changing, so you don't notice that. So it will look like constant. And
so you can assume approximately constant.
Yes.
Yeah.
Okay, thank you. And I noticed there are also some questions regarding channel estimation, and I think these will be clarified later. I have a personal question regarding one of the slides you guys mentioned about the VOFDM, which I'm really curious.
Okay.
Could you please elaborate on it a little bit more? Because I also noticed that VOFDM share very similar transmitter structures with OTFS. So what?
So it's a story. So it's a story that when we were working on this at the initial for the first few years, and one of our students, Raviteja, think he invented something. And then we did a search, find out what he invented is just a VOFDM, also called AOFDM. So that's why, and we further did a study about this structure and find out it is the ZAG transform. So the OTFS simplified version, it's equivalent to that. But that is because these 2 previous work was proposed for static multi-path channel only. So the input-output relation and the receiver structure are different.
I see.
So
but they are a pre-coding.
MMSE based.
They are a eventually this VOFDM or AOFDM is a pre-coding across subcarriers for OFDM. Okay, and but the special pre-coding matrices, if you want, that mix up the subcarriers, give you the diversity gain, which is the advantage of using VOFDM. But then you face a much more complex detection, because you can't do single tap equalization, because you have to do joint equalization of a bunch of subcarriers together. And that's where they were using just an MMSE receiver for that, which works a bit, but you can get even more if you use the OTFS like receiver, because that's much better than MMSE in terms of diversity gain. As you know, when in MIMO, MMSE receivers, plain MMSE won't give you the diversity gain, but if you do let's say a better receiver, whatever you choose, iterative, message passing, anything, it will perform much better than the pure MMSE. So same thing was here. We kind of had this problem. We had this question, and I think it's in the chat by someone. So what happens to OTFS when there is no Doppler? Okay, it's gonna work as good as VOFDM.
Yeah, it is published in this 2019
so we did write this paper on performance on static multipath channel. That means we had that curiosity.
Yeah, the multipath channel without the Doppler.
Yes. Okay. Thank you very much for the answers. I think since pretty much all the questions have been answered, maybe we can go further and we can have another round of answering later. Thank you.
So I will talk very briefly channel estimation, and then Emanuele talk about detection. Maybe we can answer some questions.
Yeah, also briefly, I think we are running a bit out of time.
So then let's talk about these three parts altogether, and then finally answer the question. How about that?
Yes.
Okay, so I will give very brief introduction on OTFS channel estimation. And OTFS channel estimation is a very important problem, and also is very interesting. And there is so many different approaches in the literature. For example, channel estimation using a single embedded pilot, or superimposed pilots, or sequence-based channel estimation, or different domain-based channel estimation involving, for example, delay-Doppler, or delay time, or time frequency, etc. So due to time limitation, I will only talk about our formal work on the embedded pilot channel estimation in delay-Doppler domain. So to give you a sketch of the idea, I show you an example about 2x1 MIMO OTFS as shown in this figure. So left-hand side, the transmitter side, the right-hand side is the receiver side, in the middle of the two distinct delay-Doppler channel responses. So at the transmitter, for each antenna, we place a pilot, and we're gonna make sure this both pilot has sufficient spacing in between. And then we transmit both pilots over the distinct delay-Doppler channels with the channel response shown here. So at the receiver, we received the spreaded pilots in the delay-Doppler domain. And then the pilot spreading patterns are exactly following the corresponding delay-Doppler channel responses. So then we decide to do the threshold-based channel estimation. That means we set a threshold. We compare the magnitude of the spreaded, the magnitude of the spreaded impulses. And if the magnitudes are greater than the threshold, then those paths are taken into account. Otherwise, we simply discard these paths. Okay, so once we take into account the valid path, and according to the magnitude and the location in the delay-Doppler domain, we'll be able to estimate the channel parameters. So this is a quick sketch of the idea of the channel estimation. So this channel estimation example involves the pilot symbol placing. So in reality, of course, we also cared about the data symbol arrangement. So that motivates us to propose the transmit symbol arrangement for the CISO OTFS, as shown in figure A. So this is in delay-Doppler domain. Horizontal axis is the delay axis, vertical is the Doppler axis. So, for example, we can place the pilot in this blue grid, and the red grid, we place zero guard symbols, and the black grids, data symbols. So the key is that when we place zero guard symbols, we're going to make sure they covered the sufficient regions along delay and the Doppler axis, so that to avoid potential interference between the spreaded pilot and spreaded data symbols. For instance, if we place pilot in the delay location LP and in the Doppler location KP, so then we're gonna make sure that zero guard symbols expand at least LP minus or plus L tau. L tau is the delay tab associated with the maximum delay. So similarly, along Doppler axis, so given the pilot location KP, we're going to make sure to place zero guard symbols along KP plus minus 2 kV. kV is the delay tab, Doppler tab associated with maximum Doppler. So in this way, this complete the transmit symbol arrangement. Then we move on to the receiver side. As shown in figure B, the blue grids include the spreaded pilots, and the data symbols are outside. So based on the spreaded pilot, basically we can do the channel estimation and estimate the CSI. And based on this CSI, we can use the remaining data to do data detection. And in this way, we can do channel estimation and data detection in one OTFS frame. So I'll pass to Emanuele for detection.
Okay. Okay, next slide. Then we'll talk about how to extract the transmitted OFDM, the transmitted QAM modulated symbols, which are arranged in the matrix X. And because of the two-dimensional twisted convolution relation, we will have MN equations of this type. For each received sample Y in the delay-Doppler, we've seen it's the result of this 2D twisted convolution. So if you arrange all these equations with noise in a matrix form, you have your vectorized symbols received samples in the delay-Doppler domain in the vector Y, times the matrix H that E described before, which is a sparse matrix, times X. Okay, and in that sparse matrix, we include the phase corrections of the twisted convolution. So you remember there were only P non-zero elements, then they, depending on where they are, they will have a different phase. So if you put those in, you have this canonical problem of detection problem of X given the observations Y, and we initially attack this problem with message passing techniques, but today I will talk about the MRC detection method, which is simply much simpler to implement than message passing. Next slide. Sorry, next slide. Okay. Too fast. Previous slide. Slide 32. Thank you. So the detection complexity of this maximum ratio combining detection is much lower than the message passing, but it reaches the same performance of message passing. And we can see that you can effectively benefit from the delay time implementation of this detection, because that gives you the lowest complexity of all detectors. We will present it for the ZP OTFS, where you have a zero padding between each block in the frame, but which is anyway something that's needed to allow for pilots to be placed. So we will just see that case, but because it's easier to explain, but you can find this method works equivalently well for all the variants of OTFS. The reference there give you some the details of this presentation. Next slide. So the ZP-OTFS means that we have we put zeros, all zeros in the bottom Lmax rows of the X of the delay-Doppler domain where you put the data. Okay. If you do that, then the IFFT across each row will stay 0, and when you do the vectorization of the green matrix, which is the delay time, you get this, which means you can see how you get the 0 padding appearing between each block. So next slide. Next slide. Yeah. So how does the H matrix look like? This is Y. This is the vector Y times this big H matrix times the vector X. So how we partition how we vectorize the delay-Doppler matrices, we vectorize them row by row, and so these are of length n. Each one of these subvectors of length n, and there are m of them. And the matrix H has this nice structure, which has blocks of size n by n, which are actually circulant blocks. Oh, we've lost. I think I'll need to share my screen then.
Yes, please.
Oh, I think he is coming back. Okay. Okay, thank you. Yeah. So those blocks n by n block matrices, which we identify with the matrix KML, they are actually circulant matrices, and what you have in each column is the shift of the first column and so on, circulant matrix, and these are represent the delay-Doppler. They have a non-zero element in the delay-Doppler from the delay-Doppler domain. Now, when you write that, when you see the matrix equation from before in terms of a graph, you can see how you compute y0 is just x0 times the block k00. y1 is the x0 times k11 and plus x1 k10 and so on. So this is the just graphical representation of that matrix vector multiplication, but it highlights the structure, which is helpful for the decoder in the next slide. Yeah, thanks. So here I still have the channel. Basically, we have the transmitted symbol, our x's. We have the zero padded symbols there, which are the rows. These are vectors, okay? These are variable here are the unknowns, and they are vectors, and all these are n by n matrices. So you receive the y's, the vectors y. Now, what happens is within these, let's call these the observations. When we observe, for example, y2, this contains information about x0, x1, and x2. But on the other hand, if you want to know, if you try to estimate, let's say x2, you can use the observation y2, y3, and y4 because they all contain some information about x0. So what is the idea is to combine the y2, y3, and y4 to estimate x2, because if we combine it properly. And the other idea is that because we already estimated the previous variables, the x0 and x1, we can subtract that part from the equations in giving y2 and y3, and then combine the remaining part in using the maximum ratio combining criterion, which is the optimal way of combining these observations. Even though they are correlated, it's still the best combination you can do. So it's a combination of decision feedback equalization, vector decision feedback equalization, MRC combining, and then of course you can iterate this operation multiple times. So every time you may improve your estimates in the first pass of these previous variables, and you subtract them and you iterate. So that's just the high level idea of the MRC. The good news is in the next slide, I think I can show you some performance curves. Well, the complexity, well, first of all, the complexity is just NM times L, where L is the number of delays, not the total number of paths. So that's one big gain, because we can have a lot of Dopplers in one delay, and that doesn't matter because we are working on these vectors of x0, xm vectors, which are contain all the Dopplers together. Okay, they're in one row. You see all the Dopplers together. This, by the way, I see many questions about what happens with fractional Dopplers. This is one reason why this MRC is very convenient, because it doesn't matter if you have fractional Dopplers, because when you have fractional Doppler, eventually many spurious paths appear. So you would have an increase in the number of paths appearing in each delay, for each delay, because of the fractional Doppler. But because of this receiver does not care about the total number of paths, but only about the delays, then that fractional Doppler does not hurt this receiver. Whereas the message passing had the complexity which depend on the total number of paths, and even worse on the size of the QAM. So you can see here the complexity would grow very high if you had large QAM constellations. And also if you had fractional Doppler, because this P would include that expansion of the number of paths due to the fractional Doppler. Next slide. I think you have some comparison results, but I'll go very quickly. Up there you have the single tap OFDM, and down here you have the MRC performance compared to the message passing, and there are obviously different refinements, because this iterative algorithm, you can have some over relaxation parameter to fine tune, and you can make it work sometimes for 4 QAM even a bit better than message passing, but in 16 and even 64 QAM you get exactly performance of message passing. Okay, and you can find the code for how the MRC detection works from here. But the good news is that it's simple enough to be comparable to the effort you would have to do in an OFDM system to try to fix the problem of ICI. Okay, so that's maybe why it becomes from the point of view of complexity, probably we should not be biased by the message passing, which was our first attempt, to decode, to do detection for OTFS, but had this complexity issue. So I think this MRC detection cannot be simpler, I would say, because the order of complexity is M, N, and L. So also you can find MATLAB codes about, in general, OTFS, transmitter, channel, and detection in our website. Okay, next slide. So these are just two other side directions we took on OTFS. One was OTSM, so delay sequence modulation, where effectively we just replaced the Fourier transform the discrete Fourier transform with the Walsh-Hadamard transforms. The advantage of this is very high, because the complexity of doing Walsh-Hadamard, because they are plus and minus one matrices, is that you have no complex multiplication to perform, which you need in DFTs. So that's one big advantage. And you get the surprising thing is that the performance is basically equivalent to OTFS, although it's not delay-Doppler domain. It's the time sequency domain that we are looking at. And the other paper is just generalizing the MRC detection for all OTFS variants and all fractional and delay-Doppler. You can handle all those fractional cases as well. I think that's all for detection. And E, what's the plan? Oh, we have a lot of questions. Maybe we should take some questions now. I have a long one here.
Yes, please.
Okay, I would like to know your opinion regarding resource allocation in new waveform domains, namely delay-Doppler domain, delay sequence, and delay scale domain. According to my recent research, the policy of power allocation in delay-Doppler for OTFS and OFDM and DSC is completely against the time frequency domain. Absolutely, it's not compatible with the time frequency domain. So I think OTFS will be compatible with a time division policy rather than because then you can allocate different time slots. But otherwise, if you allow all users to overlap on the entire bandwidth, because OTFS obviously spreads the signal over the entire bandwidth and the entire time, as you've seen there. So you cannot really chop up the time and bandwidth resources in the same way. So if I'm thinking of methods to allocate multiple users, the resources to multiple users, I can only think of them in time domain. I can allocate time, or I could allocate parts of bandwidth. But then whenever you reduce the time frequency plane, you lose some of the resolution of your delay in your delay-Doppler domain. So there is a price to pay in doing that. Sorry, it's a long answer. Maybe I'll take down a few. I'll take a copy of all the questions. The ones I couldn't answer tonight, I'll maybe write them. And I don't know if you plan to post the chat in somewhere in our web.
I think we missed some questions about about MRC. There is a question said, do we still need message passing? We don't do message passing.
No, you don't need anymore.
Do we still have error propagation problem? Error propagation. So he wants you to comment on error propagation.
Oh, error propagation. As any decision feedback type of equalizer, there can be error propagation, and that's where we can do concatenation with an outer code, like coded OTFS, and there you can do a turbo equalizer and decoder, and that gives enormous gains. You can probably check the references in the slide to see the turbo MRC detection.
Yeah, I also noticed there's a question regarding the fractional Doppler in channel estimation, especially for underwater applications. Is there a better way?
Right. So trying to estimate the fractional Doppler accurately is very challenging, because even if you get it wrong, it spreads in a bad way. So I would not recommend to try to estimate the actual fractional value, because it's a real number and you can only get an approximation. Rather, working in the delay-Doppler domain, where you can only see discrete samples in your channel. So with those discrete samples, you may find those additional paths, call them ghost paths or echo paths, because of the fractional Doppler. And that's where at least you can decide the ones you see above the noise floor, you detect them with that, for example, as he explained before, with the threshold detection. You will see, if you see a path sticking out from the noise floor, you decide it's a path. If it's smaller, then you can ignore it because it's below the noise floor and you will not see it. So in that way, at least you see the important paths that you want to, let's say, take into account into your detection. And any other term that if you don't see it coming up in the delay-Doppler domain on the grid, it's not there. Practically, you cannot do anything about it. It will add to your noise floor, and that's where you have to work with. So if you try, I mean, it's possible in principle to estimate the fractional Doppler, but you will find that the residual error on that fractional Doppler estimation is big enough that if you look at the value of the Doppler at one place and it's the wrong frequency, if you have a sine wave and you let it run long enough with a slightly different frequency, it will be completely misaligned after a few periods. And even if the frequency variation is very small. And that error can cause that problem. So it's not really effective when you do that to try to estimate that fractional Doppler exactly. Just take the result of the fractional Doppler on your grid points. That's my suggestion on that.
I also noticed
so
there are
there's
two.
some.
Yeah, please.
Freya, go ahead.
Yeah, I also noticed there are some questions regarding this. For example, MRC algorithm, and if it's applicable to RCP versions of OTFS reduced CP, and also its performance comparison with a ZP OTFS.
Yeah, so you can find more about that in the paper on this input-output relation, and for all variants and fractional Dopplers, and in general they will give similar performance. I don't think we ever really compared the different variants among each other, because effectively they have slightly different spectral efficiency.
Yeah, so you need to change CP, because
them.
RCP you only have one, and then ZP or CP you have each block you have. So you're gonna tune the spectral efficiency to be the same, and the same spectral efficiency you will compare BER. If you don't tune, that is basically performance and the slightly different spectral efficiency.
Yes. And
yeah,
I think there's another question. It's about this OTSM and the OTFS.
Yes, I can comment on that. Thank you. That's an interesting point.
Yes.
In fact, I agree. We should think about the delay sequence channel representation. So the actual thing that there is no physical meaning of the delay sequence channel representation, but when you take the sequence, the Walsh-Hadamard, the basis functions, they are, and you look at their spectrum, they peak at a number of frequencies, which is about the logarithm of n. So if you have the Walsh-Hadamard of n, you will find that the Fourier transform of Walsh-Hadamard have only peaks in about log n locations. So it is still a sparse representation. The basis, the Walsh-Hadamard basis function, have a corresponding sparse representation even in the frequency domain. So that's the only thing I can connect to, but to interpret the meaning of the sequency domain. But to be fair, there is no physical meaning for the channel, to represent the channel in there. It's just a different basis that we choose to project our channel, and maybe it's not so physically meaningful. But
yeah, so it
does work.
I think
it does
it's
work
easier to understand. Yeah.
Sorry.
Understand as a pre-coded scheme is easier to understand through pre-coding that way. We can see it's a WHT based pre-coded scheme. I think that because the sequence domain, the physical meaning is not strong. So I think it would be make sense to understand from pre-coding point of view.
But sequencing was the term used by the Walsh-Hadamard.
Yeah, that's true.
So that was there. It's just that it doesn't. So it has to do with the number of zero crossings. It has to do with the number of zero crossings of the Walsh-Hadamard function, basis function. So they all have a number of zero crossings, and that's the sequencing.
Yes. Okay. Thank you very much for this presentation. I noticed there are also some other questions, but they are a bit specific. So I would suggest the audience to send me some emails regarding some unresolved questions, so I can organize and summarize and send it to Professor Viterbo and Professor Hong for further answering. And especially because due to the time limitation we have today, it's already been roughly 2 hours, and given the time in Melbourne.
I will have a few slides to talk about. I will keep it as short as possible.
Oh, no worries. I thought, I'm so sorry. Yeah, please go on. Yes.
So I will talk about OTFS in Leo SATCOM. So Leo SATCOM is basically Leo SATCOM naturally fits in the high mobility scenarios that introduced by Emanuele at the beginning of the talk. So we were interested in studying the performance of OTFS in Leo SATCOM. So of course, there's in the literature, there's a number of OTFS based Leo SATCOM studies. So I just list a few initial studies. So in this talk, I mainly will talk about our work that first published in ICC workshop with Amit and Kwa, and later we extended to the TVT transaction. So to introduce that part of work, I first briefing you the Leo satellite. So Leo satellites circle the Earth at an altitude of 500 to 2,000 kilometers, and the satellites orbit the Earth at the speed of 7 to 8 kilometers per second. For example, a Leo satellite velocity at 1,500 kilometers altitude is 7.1172 kilometers per second. When the carrier frequency is 20 gigahertz with K-band, the maximum Doppler shift can be up to 400 kilohertz. So then next, I will talk about our initial studies in OTFS in Leo SATCOM. So we first consider Leo satellite is communicating with the ground UE, and both of them are in high mobility motion. And the ground UE is surrounded by a large number of high-speed moving objects acting as scatterers, which introduce the channel severe Doppler shifts. So under such setting, we first formulate the channel response model, which we have chosen the standard delay-Doppler channel response of multipath channel P-path, as I introduced at the beginning of the talk. And then we also narrow down to the delay types, which we taken from 3GPP standard NTN TDL channel model. TI, tau I is basically the product of tau I norm and DS desire. Tau I norm is additional delay over the first arrival delay, and DS desire is the scaling parameter that make the delay spread value span the range in the channel measurement corresponding some typical 5G scenarios. So it depends on your scenarios, you can choose DS desire parameter differently. Then we move on to talk about the Doppler shift. So Doppler shift we have chosen from 3GPP standard as the basic one. So the frequency part involved carrier frequency FC and the satellite, Doppler frequency incurred by satellite motion Fset. So Fset is given here. So it's a standard Doppler shift computations. In particular, I just want to clarify what is Vset cosine theta. And that was shown in this diagram. For example, this satellite is moving in this direction with the velocity Vset. And with respect to the propagation line between satellite and UE, so the satellite motion is in the angle of theta. So Vset cosine theta is the satellite speed along this propagation line. And using this speed times carrier frequency divided by speed of the light gives you the Fset. So this completes the frequency part. And then next we move to the V cosine alpha cosine phi. So how do we understand this? It is shown in this figure. So the U is the velocity is V, and the phase, the angles between the UE's motion with and the projection plane of the satellite. This angle is phi, and alpha is the satellite elevation angle. So V cosine phi cosine alpha is the UE's speed along this propagation line, and using this speed times this frequency and divide by the speed of light gives you the Doppler shift. Then we apply this to all the taps. So that is the channel part. Then we narrow down to derive the input-output relation for CISO and MIMO OTFS in time domain. So in time domain, the CISO input-output relation is the one I introduced before, is the channel matrix multiplies with the transmitted signal vector. And the channel matrix G is given here. And similarly, you can write down the MIMO OTFS input-output relation. So in particular, the channel matrix G MIMO is given here. So here we assume that the MIMO system has NT transmit and NR receive antennas. So basically, it forms NT-NR links, okay? And then each link basically has the channel matrix G, which follows the CISO case, the channel matrix format. So to simplify this, all these derivations, we further assume that all MIMO links share the same number of paths, P, and also each path have the same delay index Li and Doppler index Ki. So under this assumption, so the MIMO channel matrix can be reduced to the right-hand side version, which is summation over P path. And each path, we have a collection of MIMO path gains, is called the matrix HI, and Kronecker with delay and Doppler matrices. So, and then we further studied the spatial correlation, actually the antenna correlation impact on this MIMO OTFS. So I skip all the details and the detailed derivation. Instead, I will just comment on the correlation impact. So basically the impact will be on the MIMO path gain channel HI. So it will introduce some correlation to this MIMO path gain. And in this ICC paper, we basically did a whitening transformation to remove the spatial correlation on the channel. So I skip all the detailed derivation. Derivation can be found in these two papers. So instead, I will just directly show you the simulation result. So we basically did the simulation using the parameters as shown in the table. And we also applied the message passing detection. So in figure A, we compare the OTFS performance versus OFDM performance. So the pink curves represent OFDM performance, and the blue curve represent OTFS performance. And the dashed line represent the CISO case, solid line represent the MIMO case. As shown in this figure, so basically OTFS in such a setting has better performance. Then we move to figure B, where we demonstrate the impact of antenna correlation on this 2x2 MIMO OTFS system. So we also showed that MIMO OTFS without any antenna correlation as the black solid line as a benchmark. So then we also evaluated the MIMO OTFS with antenna correlation. The red one is with high antenna correlation factor 0.8, and the other is with lower antenna correlation factor 0.2. And then we applied the whitening transformation that demonstrate that in particular for the low antenna correlation case, can have significant performance improvement, which is close to the no correlation case. So this is the initial work we published in ICC, and then we further expanded with a lot of other like error performance and theoretical derivation on this SNR comparison, receiver SNR comparison, and generated these TVT transactions. So then I will leave the most important conclusion and application to Emanuele.
Okay, thank you. Just final slide. We just went through a very quick overview of OTFS, where we believe there are some very interesting applications of OTFS is for non-terrestrial networks. So this is definitely, we've seen the satellite, but combining the mobility of the high mobility of the satellites and the ground mobility, or whatever flying cars there may be, that will be an interesting case where it is the high mobility assumption is absolutely there, and there is no way OFDM will cope with that. Another very important thing is using OTFS for sensing and localization as a technique, as a radar waveform. And then even better in the integrated sensing and communication settings, because you can do at the same time channel estimation and learn the range and velocity of the scatters in the channel. So you can see there is an immediate benefit of reusing the communication signal waveform to actually estimate range and velocity of that. The other interesting place we've seen is underwater communications, and the challenge, why is it really interesting there? Because the speed of light that we have in electromagnetic waves in air is 3 times 10 to the 8 meters per second, while in underwater is maybe just 1,500 meters per second, which is much slower, which means that your even low speed moving vessels underwater will generate a very large Doppler shifts, and that's an interesting case. There are some recent papers applying machine learning in OTFS, and maybe many more papers. I hope we will hear from the next talks in the seminar series, and we'll have some interesting conversations. So I think that concludes our talk. I thank you for staying so long, and sorry for going too long.
No, thank you, Emanuele and Yi. Thanks for the presentation. I'm sorry that I thought like it was finished previously, but it's wonderful that you guys talk about the satellite communications and give a nice conclusion and applications. To be honest, I have some questions to ask, especially for this LEO satellite scenario. If I understand correctly, so there will be a dominant path, right, for satellite communication. If there's not so many multi-paths, do you think OTFS or delay-Doppler waveforms can still play some advantages in this case?
Well, imagine sorry, you go.
You go. So in our initial study, we considered TTL. So if you check NTN for satellite, this standard, so they have different channel models. So it depends on different scenario and different channel models. I think we just did this simulation based and then antenna correlation based research. I think there is a much more research to be studied. For example, like NTN, this multi-transmission. cooperative
multiple
transmission
satellite,
that
cooperative,
multiple satellite aiding to provide service to ground users. And I think I will pass Emanuele to talk. I know
this maybe the scenario
topic.
Okay, the scenario where I agree there is one dominant path, but even if you have two paths, the moment you have two paths which are there, you will need to use OTFS, because imagine you have two satellites and your ground receiver is seeing two satellites. One is flying over on one side and the other one is coming on the right hand side, and the other one is going. So you have two paths coming in with huge Doppler difference, and they will generate a huge Doppler spread. Okay, and that Doppler spread will be very hard to equalize if you don't do OTFS. So there are, and although maybe the big Doppler from one is not that big, because ultimately it's coming from the ground scatterers, and maybe they are, which are moving, or a swarm of flying cars or UAVs, and they are all moving. In those scenarios, maybe yes, but really a practical one, I think, is the NTN network with multiple operating satellites to connect to ground stations.
Right. Thank you. Speaking of the Doppler spread, I agree with you. If there are some relative motions between different objects, of course, the Doppler will be very high. Then this will cause another problem, because OTFS, they are, if I understand correctly, it assumes the underspread channel, right? So that means the maximum Doppler is smaller than the bandwidth, subcarrier spacing. If the Doppler is so large, how much bandwidth do we need to cope with this?
You may want to reduce your Doppler resolution to and obviously
I think in LEO satellite, LEO satellite has 400, for example. I showed the example 400 kilohertz. This, so typically they prefer to do a pre-compensation.
Right, but if there's multipass,
if you have two satellites, then you may have a plus 400 kilohertz and a minus 400 kilohertz.
Yeah, that's true.
Good luck with that, And there, obviously, for OTFS to work, you need that the Doppler spread of the channel to be less than the delta F, the spacing between the subcarriers. Okay. Right. So that's the condition. And I think probably there will be a talk by Saif or Chox about the crystallization conditions, and those relate exactly to the limit of where OTFS works, and it's exactly, there is a maximum delay spread and a maximum Doppler spread for which it works. And same as again.
You can maybe you can have over spread channels with large Doppler or large delay.
Right.
Yeah. That typically can happen in LEO or even underwater communication.
That's right. That's right. Thank you very much. I think that's a really great answers to this satellite communications. And yes, given the time being that and especially the time in Melbourne, I think we may conclude for today. And there will be other questions from the audience. And if you are more than welcome to send email to me, and I'll summarize all the questions, including the ones we have in the meeting chat, and send them to the presenters, and we can have the answers afterwards. And I'll send you guys emails for the updates. Okay. And thank you again for joining us for today, and especially great thanks to Emanuele and Yi for the wonderful speak today. And our next speaker will be Professor Saif, Professor Roni Hadani, and also Professor Chox and Robert Calderbank for the OTFS 2.0, and we'll announce the details once the time approaches. And thank you again for joining us. Feel free to drop me an email for the further questions.
So thank you, Shuanyang, for organizing this wonderful series. Thank you very much for your effort.
Thank you for joining us. Yeah. And
thank
see you guys.
Thank you all.
Thank you.
Bye.
Thank you. Bye bye.